Okay, here we go. We just discovered some amazing things. Mind-blowing why they're named hyperbolic functions. But okay, it's time to move on. It's time to investigate the derivatives. Starting with, what is the derivative of sinh x? Turns out it won't be too difficult to figure out. We can show it all on the screen here. Going back to the definition of sinh x, e to the x minus e to the negative x over 2. If we just take the derivative of that, we'll have it. You kind of think like the derivative of sinh x, like, will the connection to the trig derivatives be here? Like, wouldn't it be great if the derivative of sinh x was cosh x? Wouldn't that be incredible? Let's see what happens. So e to the x minus e to the negative x over 2. So the fact that we're dividing by 2, let's factor that out as a 1/2. It's a constant. We can just take that right out of the derivative, and we can just focus on the derivative of e to the x minus e to the negative x. No problem. We know how to take the derivative of that. The derivative of e to the x is, of course, just e to the x. The derivative of e to the negative x, be careful, you need a chain rule there. You need to multiply, after copying, you then need to multiply by the derivative of the negative x, which is -1. So minus e to the negative x times -1. Of course, that minus and that -1 make a positive, e to the x plus e to the negative x, and the 1/2 is still up front. Let's turn it back into a fraction. And maybe you recognize that, e to the x plus e to the negative x over 2. And wouldn't you know it, that is cosh x. Oh my goodness, that's incredible. Amazing. So another connection to the trig there with the derivative. Okay. Well, let's investigate the derivative of cosh x. Wouldn't it be amazing if this turned out to be negative sinh x? Just like the trig. Let's see. It's not going to be too difficult to figure out. E to the x plus e to the negative x over 2. We'll go through very similar steps. Take the 1/2 out. Okay. Take the derivative. Again, we've got the chain rule happening on e to the negative x. So e to the negative x times -1. And that just simplifies to a subtraction, e to the x minus e to the negative x. With the 1/2, it's e to the x minus e to the negative x over 2. Oh, wow. Wait a second. What is that? That's exactly sinh x. Okay, so the derivative of cosh x is positive sinh x. Really interesting. So in one sense, like if you were to take multiple derivatives, they'd just go back and forth between each other, wouldn't they? Okay, let me just tell you the rest of them here. Here are the hyperbolic derivatives, and it turns out they are really, really close to the trig derivatives. There's just 2 of them where there's one little difference. So derivative of sinh x is cosh x, derivative of cosh x is sinh x. So there's one of the differences, and there's not a minus there, it's positive. Derivative of tanh x is sech squared x, just like we would hope and kind of want it to be. It is. The derivative of cosech x is negative cosech x coth x. Perfect. Just like the trig derivative. Here's the other little change for derivative sech x. Turns out this one is negative sech x tanh x. So it's almost like this one was negative, now it's positive. This one was positive, now it's negative. Otherwise, they're all exactly the same. Derivative of coth x is negative cosech squared x. So all the same friendships are there, the same patterns. It's just that now the first 3 are all positive and the second 3 are all negative. Okay. So you notice I left some space here at the bottom. Okay, so it turns out, I hate to do this to you, but it turns out all 6 of these hyperbolic functions also have inverses, and all of those inverses have derivatives as well. So here you go. Here are the inverse hyperbolic derivatives. And these, are not as friendly, kind of like, they kind of remind us of the inverse trig derivatives. They're all like these fractions with square roots involved, and that's the way it goes. So wow, I just like dropped 12 derivatives on you here at the end of this section. Well, that's just how it is. Okay, let's talk about these last few. These are not so easy to remember. There's not like the same patterns. If you look at derivative of inverse sinh x, 1 over square root 1 plus x squared. The derivative of inverse sine x is 1 over 1 minus x squared. So that minus turned to a plus. But the derivative of inverse cosh x is quite a bit different. So there it is, 1 over square root x squared minus 1. Derivative of inverse tanh x, this one changed a plus to a minus as well. So derivative of inverse tangent was 1 over 1 plus x squared. So here it turns to a minus. I don't know if that makes it easier or worse to remember when it's like really close, but not quite. These guys, oh man, inverse cosesh x, -1 over the absolute value of square root x squared plus 1. Oh man. And inverse sesh x, also negative, not an absolute value, just x square root 1 minus x squared. And you kind of see a connection between this square root and this square root. And then here you're subtracting. Now you switch the places, but okay. And then finally notice inverse coth x derivative 1 over 1 minus x squared. It's the same as inverse tanch's derivative. I think, what's up with that? Well, it turns out the domain of these derivatives would be different. So we wouldn't use the same x values here as we would here. We won't go into the details of the domains of these derivatives. I think we can leave that alone. But yes, they are equal in a sense, but they wouldn't apply to the same x values. Okay, we won't do any examples of these. Jump into homework and do plenty of derivatives right now. These could combine with product rules or chain rules or anything like that. And that's it.